There is food provided just outside the doors here, but if you go further along the corridor to the Marsden room, there's more food available there. The second announcement relates to the red and blue dots that are available on the tables. And these are for people to vote for the best posters. So when you get the opportunity to have a look at the posters, they're located in the back of this room. We'd ask you to just place some of those dots on the best poster. And you're not allowed to steal other people's dots, and you're not allowed to take dots off posters. Okay, so we'll kick off this session. It's entitled Cardiovascular Development and Disease Modelling. And I'd like to introduce our first speaker, who's also the co-convener of this extraordinary meeting. I'd like to invite Zhang. The title of his talk is The Convergence of Life Sciences and Engineering, Human hiPSC to Rebuild the Failing Heart, Roadblocks to be Overcome. Thank you.
Good morning. So I want to take the opportunity to thank the host to put this fantastic meeting together. The venue is fantastic. The Australian colleagues are very, very warm and collegial. I thank you very much. And I also want to take the opportunity to thank my colleagues all over the world from North America, from Europe, from Japan, from China, came all have overcome all the jet lag, come to attend this morning's meeting. So I want to take the next, I try to make it 18 minutes, save 2 minutes to answer the question. I usually give a provocative talk. So again, I will try to provoke people to ask questions, and I want to have a very active discussion with you. So the title is Convergence of Life Science and Engineering. The science are exciting, putting all the energy and people together, but science does not change life. Science have to combine with engineering to change life. So everybody have iPhone. iPhone is the good example of technology and engineering that change everybody's life. So I'm going to also go back 25 years to talk about the cardiovascular science and convergence of life science and engineering. So this is the one of the major problem in life science, that is the post-infarction LV remodeling, as shown on this slide. Arrow points to a thin piece of scar during systole. This LV bulging pulled, overstretched the border zone on my side. I think the elongation, this is old study in 1996, so the pig heart, normal myocyte, disaggregate myocyte is about 120 micron in length, and the failing heart is twice as long. So in this, let's see. In this viewpoint, I put a provocative concept. I'm telling my colleagues that the failing heart myocyte is not ischemia. It's the elongation pull is causing the problem. So the model we use is the pig model post-infarction LV remodeling and congestive heart failure, as shown here. The left side is sham operated normal, and on the right side is the heart, is the animal with LCX ligation induced mitral regurgitation and dilatation with end stage heart failure, as shown here. And so this is the pericardial effusion. The normal heart, as most of you know, that there's no significant fluid in the pericardial sac, but in the failing heart, there's as shown on this slide, there's significant pericardial effusion indicate the end stage of a congestive heart failure. This is the four-chamber view of the pig heart at the end stage of heart failure. So in this study we published earlier in 2012, we conveyed the concept that the energetic state, PCR-ATP ratio as shown here, the protein phosphate PCR, and the 3-phosphorescence of ATP, the PCR-ATP ratio representing the energetic of the machinery of the heart. In normal heart, this ratio is about 2. In the failing heart, it's decreased significantly in about 1.5. But this study, we want to convey the concept that the heart is an inhomogeneous organ. You have to know that in the periscar border zone, PCR-ATP ratio is much lower than the remote area. In normal heart, this PCR-ATP ratio is about 2, decreased to 1.5. In the remote zone is decreased about 1 in the border zone. This is color-coded. It's the technology that we can have one shot of 15 minutes to acquire the 20 spectrum across the border, infra zone, border zone, and remote zone. In the early study, and this is a circulation 2013, we used the engineering technology to mapping the mitochondrial ATP machinery by measure the ATPase, the flux of ATP, the generation of ATP for the first time we can measure with the NMR spectroscopy with a precision of micromolar per second. So this is the study, have 8 normal hearts with red with a bracket, and the ones with myocardial infarction only is the triangular, it's showing here, and the ones with the cell patch are showing in the field circle as shown here. So the cell patch prevent LV bulging as shown on this slide, that LV bulging during systole in myocardial infarction only was effectively prevented by the cell patch transplantation as shown here. So when we plot each heart, the ATP flux rate versus the LV dilatation, in here we measured by the mapping of the wall stress, there's a linear relationship of decrease of ATP flux is linearly related with the increase of wall stress. So for the first time, we can measure the myocardial ATP flux rate, which is about 1, in normal heart, it's about 1 micromoles per gram per second, as shown here, which translates the normal heart utilize 10 kilogram of ATP every day. Previously, we used the oxygen consumption with the PO ratio of 3 to measure almost identical the ATP consumption rate. So this is direct measurement of the ATP flux rate. So again, the engineering changed the assessment of the heart failure. So I will take the next 5 minutes to talk about myocardial tissue engineering as one of the major roadblock, as we know that is the low engulfing rate. So 4 weeks after the cell transplantation, the engulfing rate is less than 1%. We have done hundreds of pigs and thousands of I've done thousands of dogs study also. So the engraftment rate usually is less than 1% after the 4 weeks after the transplantation. So how to overcome that? This is a recent publication in the Circulation Research in 2018. We used the MHC-driven overexpression of cyclin D2, as shown here. So cyclin D2, this is a human cardiac fibroblast-derived iPS cell with human MHC-driven overexpression cyclin D2. Western blot demonstrated successful of expression of cyclin D2 in the cell line. So only the cells differentiate to myocyte that overexpress cyclin D2 here. And in vitro, the myocyte proliferation increased about 8-fold, as shown here, showing the Aurora B indicates the cell Aurora B is a protein of the function of the attachment of the mitotic spindle in the centromere, as shown here. The Aurora B indicates in vitro myocyte proliferation is increased 8-fold compared to wild type. And in vivo, when this myocyte transplantation into the rodent heart, immunodeficient rodent heart, 4 weeks after the transplantation, the wild type only have less than single-digit cell engraftment rate. However, in the heart received cyclin D2 overexpression, there's a significant human muscle cell in the rodent heart, as shown here. So this is a human-specific cardiac troponin T 4 weeks after transplantation. And I just use this as showing another assessment. The white is the human-specific nuclear antigen, again showing significant remuscularization of the rodent heart received the MHC-driven overexpression cyclin D2 myocyte. So this is 4 weeks after the transplantation, and unpublished data showing here. This is the 6 months. The rodent received rodent myocardial infarction. The heart received the MHC-driven cyclin D2 overexpression myocyte 6 months after the transplantation, as shown on typical, shown on this slide, typical cross-section left ventricle showing the green is the non-specific troponin T, cardiac troponin T, and red is a human-specific cardiac troponin T. So overlay showing in yellow, and another assessment demonstrate human-specific nuclear antigen as showing white, as shown here. So this slides demonstrate that the remuscularization of injured ventricle is achieved in this technology. So we are not propose a therapy, but we propose a concept that the remuscularization is possible to promote the myocyte proliferation, as shown here. So this, again, this is 6 months after the transplantation, a significant myocyte piece is in the infarct area, as shown here. So the question now is whether this remuscularized injured ventricle is cause the arrhythmic problem. So we cannot examine decipher the mechanisms of arrhythmia in the rodent heart because rodent heart beats 600 beats per minute. It's the VT heart. So we have to use the pig that beats 100 beats per minute. As shown here, this is the in circulation. For the first time, we fabricate 4 centimeter by 2 centimeter thickness, 1.25 millimeter clinical relevant size of cardiac patch transplant into the pig heart, as shown here, the 2 by 4 centimeter surface and 1.2 millimeter thickness large myocardial patch derived from the iPSC derived myocyte endothelial cell, smooth muscle cell, and a dynamic culture. So it's important here. It's a dynamic culture will make the functional myocardium close to the naive heart. There's still lots of work to do. So this slide illustrates our EP technology. This is a 524 leads going to the computer to record propagation from base to apex, from the left to right, the action potential. The space resolution is about 1.2 millimeter. If this is not good enough, we use, this shows the this video should work. Okay. So that's the panoramic optical mapping of the entire ventricle of the pig heart to decipher the mechanisms of if the arrhythmia risk are coming from the propagation, the re-entry problem or ectopic center. That's the novel technology of the. So this is a rapid pacing induced VT. As you can see, depolarization wavefront is blue and the repolarization wavefront is gray. So over the time, the orange is the reagents of the arrhythmia. So we can decipher the mechanisms of arrhythmia and then we can engineer the cell line to prevent the re-entry arrhythmia or ectopic center. So all these are talked about the cell transplantation. But if we can make the recipient heart, that's 3 billion of myocytes go on proliferation, then we have a much powerful machinery to regenerate the injured ventricle. So this study, actually we have 2 papers published in the same volume of circulation, showing that the neonatal, large mammal neonatal in postnatal day 1, there's significant regeneration potential. We did LD ligation. At the postnatal day 1, this neonatal pig can regenerate apex, which disappeared at the postnatal day 3. So my colleague Yele will talk tomorrow more detail. I run out of time and I want to answer some questions. The study will not be possible with my student and the postdoc and colleagues day and night work and the collaborators, including the people in the room also, including Tim Camp, Burlingham. In UAB, there's Tim Towns, Jack Rogers, Fast Wilcott, and in Duke, there's Dr. Bosak, Victor Rockman, and Minnesota, there's Dr. Argo and Gary, and NIH support to for all these provocative study findings. I have a few minutes to answer questions. Thank you for your attention.
Thank you, Jay. I think we'll have time for 2 questions maybe. I'm happy to kick off with one question. With your mapping study, what did you conclude was the mechanism for the arrhythmia? Was it re-entry or automaticity or something else?
So This is an important question, whether it's the significant graft will cause the re-entry arrhythmia when the action potential pass through the interface of the graft and the recipient heart. We hypothesized that because of the conduction velocity of grafts or fabricated tissue are slower will cause re-entry, induce arrhythmia, but we did not find any of those. In the rodent heart, we found actually when the propagation passed through the recipient heart, which beats 600 beats per minute, and pass through the grafts, we show the muscular ventricle of the rodent heart, it starts to beat at 100 beats per minute, and then on top of 100 beats per minute, there's a small peaks of still beats at 600 beats per minute. So it's the integration of action potential, but that's not the action potential pass through without arrhythmia. This is in rodent heart. The pig heart, we don't have the data yet.
Okay.
But the key is we want to identify the mechanisms of potential arrhythmogenicity and engineer the cell line to have a faster propagation velocity and or lower action potential to trigger the ectopic center.
Just looking at the map that you showed, it looked like it was a figure of 8 re-entry. There was an isthmus in the middle that had slow conduction, and then loops were going around the outside and coming back through the center.
So that was a control heart. We want to demonstrate the technology. It's a pig heart. We paste it to the VT, and we want to see when the VT happened and at what time point. The spatial resolution is only a few millimeters. And this is only the surface. We have to combine the optical mapping with the electrical mapping also to have the transmural. So because the optical mapping only see the surface, and the pig heart, human heart is a few centimeters in diastole. So this is more complicated, but we will do that.
Okay. All right, thank you for the talk, Jay.